What if the mysterious object racing through our solar system isn't what it appears to be? Fresh observations of 3I/Atlas are revealing characteristics so unusual that some scientists are questioning whether we're dealing with a natural comet at all. This interstellar visitor's trajectory, timing, and behavior patterns are defying conventional explanations, leading to heated debates in the scientific community. Today, we'll examine the mounting evidence that suggests this cosmic wanderer might be far more extraordinary than anyone initially imagined, and explore the controversial possibility that we could be witnessing something truly unprecedented. Discovery and initial detection. The story of 3I/Atlas begins with a routine sky survey that would soon turn extraordinary. On July 1, 2025, the Atlas telescope system at Rio Hurtado Observatory in Chile captured images of an unusual fast-moving object designated A11PL3Z. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object. Within days, follow-up observations confirmed what astronomers had suspected. This was the third confirmed interstellar visitor in human history, joining the ranks of 1I Oumuamua discovered in 2017 and 2I Borisov found in 2019. The object received multiple designations, 3I Atlas for its interstellar status, and C2025N1 for its cometary characteristics. What made this discovery particularly intriguing was that despite entering our solar system weeks earlier, 3I Atlas had remained undetected due to its challenging viewing angle against the dense star fields near Sagittarius. John Tonry, principal investigator of the Atlas project, noted that pre-discovery images dating back to June 14, 2025 revealed the object had been silently approaching our solar system for an extended period. This late detection would prove to be just the first of many unusual characteristics that would set 3I Atlas apart from any cosmic visitor we'd ever encountered. Extraordinary orbital characteristics. Prepare to have your mind blown by the absolutely extraordinary orbital mechanics of this interstellar wanderer. Davide Farnocchia from NASA's Jet Propulsion Laboratory has calculated that 3I Atlas follows a hyperbolic orbit with an extreme eccentricity of 6.14, the highest value ever recorded for any known interstellar object. This mathematical measurement indicates just how dramatically different this visitor's path is from anything bound to our solar system. Even more remarkable is its incoming velocity of 58 kilometers per second, making it the fastest interstellar visitor ever recorded approaching our cosmic neighborhood. But here's where things get truly suspicious. The trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun. Marco Micheli from the European Space Agency has calculated that the probability of this alignment occurring by random chance is merely 0.2%. This isn't just unusual, it's astronomically improbable. Most objects from interstellar space would approach from random angles, yet 3I Atlas chose a path that seems almost deliberately designed for optimal planetary encounters. The precision of this trajectory has prompted some researchers to question whether we're witnessing natural celestial mechanics or something far more intentional. Such mathematical precision in cosmic trajectories typically requires either extraordinary coincidence or deliberate planning. Suspicious planetary encounters. The planetary encounter sequence of 3I Atlas reads like a carefully choreographed cosmic ballet that defies statistical probability. Robert Warwick from the University of Western Ontario, who previously discovered Oumuamua, has analyzed the object's path and found it passes unusually close to Venus, Mars, and Jupiter during its solar system transit. The probability of such close encounters occurring randomly has been calculated at an astounding 0.005%. Essentially impossible by chance alone. But the timing gets even more suspicious. Paul Chodas from NASA's Center for Near-Earth Object Studies has determined that 3I Atlas reaches its closest approach to the Sun precisely when Earth would be positioned on the opposite side, blocking direct observation during the most critical phase of its visit. The statistical probability of this alignment? A mere 7% chance. Karen Meach from the University of Hawaii has noted that rather than resembling the chaotic path of a randomly ejected comet, the trajectory appears optimized for studying the inner solar system planets while minimizing detection risks. This orbital choreography provides optimal vantage points for comprehensive planetary observations, exactly what you'd expect from a reconnaissance mission rather than a chance cosmic encounter. The mathematical precision required for such a trajectory suggests either unprecedented natural coincidence or deliberate design by an intelligence capable of interplanetary navigation. Physical properties and anomalies. The physical characteristics of 3I/Atlas are equally perplexing and honestly challenge our understanding of typical interstellar objects. Daryl Seligman from Michigan State University has determined that the object measures somewhere between 1 to 12 kilometers in diameter, making it significantly larger than both previous interstellar visitors and providing an unprecedented opportunity for detailed study. Spectroscopic analysis suggests this cosmic wanderer is extraordinarily ancient, potentially 7 billion years old, predating our entire solar system by billions of years. This makes it a genuine cosmic fossil, carrying secrets from the early epochs of our galaxy. Quanzi Ye from the University of Maryland has confirmed that 3I/Atlas is the brightest interstellar object ever observed, allowing for detailed spectroscopic analysis that just wasn't possible with previous visitors. Perhaps most intriguingly, the object exhibits a 29-hour rotation period with minimal brightness variation, suggesting either a spherical shape or a uniform surface composition, characteristics that are pretty unusual for natural comets. Matthew Knight from the Naval Research Laboratory has noted that high-resolution observations reveal a remarkably compact and dense appearance, lacking the typical fuzzy, diffuse structure expected from ancient comets. These physical properties suggest either an unusually well-preserved natural object or something with a fundamentally different composition and structure than anything we've previously encountered in our solar system. Comet-like features versus anomalous behavior. Here's where 3I/Atlas becomes truly enigmatic. It displays some comet-like characteristics while simultaneously exhibiting behavior that frankly just defies cometary physics. Alan Fitzsimmons from Queen's University Belfast has confirmed that the object shows a faint coma and a short tail measuring approximately 3 arc-seconds, indicating active outgassing as solar radiation heats its surface. Spectroscopic observations have detected the characteristic signature of sublimating water ice, producing the dust and gas envelope typical of approaching comets. However, Tony Farnham from the University of Maryland has noted several anomalies that challenge this interpretation. Despite its proximity to the Sun and evidence of outgassing, 3I/Atlas maintains a remarkably compact, dense appearance that differs dramatically from the fuzzy, diffuse structure of typical comets. Most puzzling is the absence of an expected extended tail, which really should be prominent given the object's size and solar distance. Bin Yang from the European Southern Observatory has observed that the outgassing patterns don't follow standard cometary models, with irregular brightness variations that suggest complex subsurface processes. The combination of active sublimation with maintained structural integrity presents a paradox. How can an object simultaneously behave like a comet while retaining characteristics more consistent with a solid engineered structure? This contradiction has sparked intense debate about whether we're observing natural cometary processes or something fundamentally different masquerading as a comet. Scientific debate: natural versus artificial. The scientific community has erupted into heated debate over the true nature of 3I/Atlas, with interpretations ranging from exotic natural phenomena to, well, potentially artificial origins. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University, has emerged as the most vocal proponent of considering artificial origins, pointing to the statistically improbable trajectory and suspicious timing as evidence that, in his view, warrants serious investigation. Loeb argues that the mathematical precision of the object's path, combined with its optimal positioning for planetary reconnaissance, exceeds reasonable expectations for random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide. However, mainstream astronomers have pushed back strongly against these suggestions. Sarah Seeger from MIT acknowledges the unusual characteristics while emphasizing the importance of exhausting natural explanations before considering extraordinary possibilities. Robert Yedecke from the University of Hawaii has criticized speculation about artificial origins as premature and potentially damaging to scientific credibility. The debate highlights fundamental questions about how we interpret anomalous data and the threshold of evidence required for paradigm-shifting discoveries. Alan Stern, principal investigator of the New Horizons mission, has noted that while the characteristics are unusual, the universe is full of phenomena that initially appear impossible until we develop a better understanding of the underlying physics. Spectral analysis mysteries. The spectroscopic data from 3Y Atlas is revealing some puzzling inconsistencies that are, honestly, challenging our understanding of interstellar object composition. Stephanie Malam from NASA Goddard Space Flight Center has been coordinating observations using the James Webb Space Telescope to conduct detailed infrared spectroscopy of the object's composition. Initial results confirm the presence of water-ice spectrum, but the patterns just don't match our expected models. Jacqueline Keene from Boston University has identified these anomalous spectral signatures, where the observed signals actually increase in regions where water-ice models predict they should decrease. This contradiction suggests either unknown compositional elements or maybe structural properties that don't conform to standard cometary models. Now the object exhibits a distinctly reddish coloration, similar to objects in our outer asteroid belt, yet its interstellar origin kind of rules out formation in our solar system. Michelle Bannister from the University of Canterbury has noted that attempts to determine precise composition are complicated by the active coma surrounding the nucleus, which creates interference in spectral measurements. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has suggested that these unusual spectral characteristics might indicate exotic ice compositions or internal structures not found in solar system objects. So, these spectroscopic mysteries really add another layer of intrigue to an already enigmatic visitor, suggesting that 3I Atlas may be composed of materials or structured in ways we just don't yet understand. Dark forest hypothesis implications. The behavior patterns of 3I Atlas align remarkably well with theoretical models of how an advanced civilization might conduct reconnaissance while avoiding detection. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, suggests that intelligent civilizations remain hidden to avoid potential threats from other species. Seth Shostak from the SETI Institute has noted that 3Y Atlas exhibits what could be interpreted as stealth-like behavior, deliberately timing its closest solar approach when Earth would be positioned to block optimal observation. This timing ensures that the most detailed study phase occurs when our planet's scientific instruments have limited access to the visitor. Jill Tarter, former director of SETI research, has observed that the trajectory allows for comprehensive surveying of inner solar system planets, while minimizing exposure to potential detection by any resident intelligence. The orbital path provides optimal vantage points for studying Earth's atmosphere, Mars's surface conditions, and Venus's cloud dynamics, exactly the type of data an exploring civilization would prioritize. Frank Drake, creator of the famous Drake equation, noted before his passing that such reconnaissance patterns would represent logical exploration strategies for risk-averse civilizations. While most scientists remain skeptical of artificial explanations, the behavioral patterns of 3I Atlas do match theoretical models of how cautious interstellar explorers might operate when encountering potentially inhabited star systems. Historical context and lessons. The discovery of 3I Atlas comes with profound lessons learned from our missed opportunities with previous interstellar visitors. When 1I Oumuamua was discovered in 2017, the scientific community was caught completely unprepared for studying such a rare phenomenon. Robert Warwick, who discovered Oumuamua using the Pan-STARRS 1 telescope, has reflected on how the object's rapid departure left many critical questions unanswered. The mysterious acceleration exhibited by Oumuamua without visible outgassing remains unexplained to this day, highlighting the importance of comprehensive observation campaigns. Gennady Borisov, the amateur astronomer who discovered 2I Borisov in 2019 from his observatory in Crimea, provided the astronomical community with a second chance that was better utilized. However, even Borisov's study was limited by available technology and coordination protocols. Mark Norris, from the University of Central Lancashire, has emphasized that 3I Atlas represents our most comprehensive opportunity yet to properly study an interstellar visitor with advanced instruments and coordinated global observation campaigns. The improved detection capabilities of modern sky surveys, combined with rapid communication networks, have enabled real-time coordination among observatories worldwide. Michelle Bannister has noted that the lessons learned from previous interstellar encounters have fundamentally changed how the astronomical community approaches these rare events, ensuring that we're better prepared to unlock the secrets these cosmic messengers carry from distant star systems. Future observations and implications. The coming months represent a critical window for determining the true nature of 3I Atlas before it departs our solar system forever. Perihelion is scheduled for October 30th, 2025, after which the object will begin its journey back toward interstellar space. Paul Chodas has calculated that 3Y Atlas will re-emerge from behind the Sun in December 2025, providing a final opportunity for detailed observations before it becomes too distant for meaningful study. Karen Meach is coordinating an unprecedented international observation campaign involving over 50 professional observatories and numerous space-based instruments. The Hubble Space Telescope, James Webb Space Telescope, and ground-based facilities including the Very Large Telescope in Chile are all dedicating precious observation time to this cosmic visitor. Daryl Seligman has noted that the data collected during this campaign will either confirm 3I Atlas as an exotic but natural interstellar comet, or potentially revolutionize our understanding of what's possible in our cosmic neighborhood. The implications extend far beyond pure astronomy. If 3I Atlas proves to be artificial, it would fundamentally alter humanity's perspective on our place in the universe and our approaches to planetary defense and interstellar communication. Alan Fitzsimmons emphasizes that regardless of the final interpretation, 3I Atlas represents a pivotal moment in astronomy, where advanced technology meets unprecedented opportunity to study materials and possibly intelligence from beyond our solar system. As 3I Atlas continues its mysterious journey through our solar system, it challenges everything we thought we knew about interstellar visitors. Whether this ancient wanderer is an exotic natural phenomenon or something far more extraordinary, it's forcing us to expand our understanding of what's possible in the cosmos. The next few months will be crucial in determining the truth about this enigmatic visitor before it disappears back into the depths of space. Stay tuned to InnoVision Tech for the latest updates on this cosmic mystery. Like, share, and subscribe. What if our first clear chance to photograph an interstellar visitor was deliberately sabotaged? On October 7, 2025, the world held its breath for a portrait of the interstellar comet 3I/Atlas as it flew past Mars. Instead, we got a blurry dot, a global controversy, and a coordinated silence from the world's leading space agencies. This wasn't just a technical glitch, it was the start of a mystery that points to something being hidden in plain sight. Let's delve into it. The blurry dot. It was supposed to be the space photo of the decade, but it looked like a mistake. At precisely 9:22 UTC on October 7, 2025, the European Space Agency released the first official image of 3I/Atlas, captured by the CASIS camera on the ExoMars Trace Gas Orbiter. The public expected the stunning high-resolution detail we've come to associate with our Martian probes. What they received was a single, fuzzy, underwhelming pixel against the blackness of space. The comet, with an apparent magnitude of +19, was incredibly faint. Within an hour, this blurry dot became a global phenomenon for all the wrong reasons. The team behind the camera, led by its principal investigator, Nicholas Thomas, from the University of Bern, knew they were pushing their instrument to its absolute limits. CASIS was designed to look down at Mars from an altitude of 400 kilometers, not out into the deep void. They had performed a complex slew maneuver, pointing the entire 4,332-kilogram spacecraft at a target 30 million kilometers away that was over 10,000 times fainter than anything the camera was built for. The resulting image wasn't a failure, but a triumph of engineering that required stacking multiple exposures to even get a detection. The world, however, didn't see a technical miracle. It saw a smudge and immediately began asking what was being hidden from view. Global outrage. The internet doesn't wait for explanations, it demands answers. The moment the blurry dot hit social media, the backlash was instantaneous and brutal. Hashtags like fuzzy dot and where are the pics trended in over 20 countries, generating more than 1 million posts on X and Reddit within 24 hours. Side-by-side comparisons showing sharper images from backyard telescopes flooded every platform, fueling a narrative of incompetence, or worse, a deliberate cover-up. Renowned science journalists like Dennis Overby of the New York Times were forced to frame the story not around the science, but around the profound public disappointment. The outrage wasn't just about a low-quality photo, it was about the perceived breach of trust. After being spoiled by the crystal-clear images from the James Webb Space Telescope and the New Horizons Pluto flyby, this blurry dot felt like a step backward, an insult to the €1.7 billion price tag of the ExoMars mission. The simultaneous silence from NASA, China, and the UAE only poured gasoline on the fire. It created a dangerous vacuum of information that was quickly filled with suspicion, turning what should have been a scientific celebration into a full-blown public relations crisis. Technical limits. So, was this a cover-up, or just the hard reality of physics? The truth is, the blurry dot was inevitable, and the numbers prove it. Let me explain. The Cassis camera, developed by a Swiss-led consortium including scientist Gabriele Cremonese, is an imaging powerhouse when pointed at Mars. From its 400-kilometer orbit, it achieves a stunning resolution of 4.5 meters per pixel. But I/Atlas was 30 million kilometers away. At that vast distance, the camera's angular resolution of 11.36 microradians per pixel translates to a pixel scale of about 340 kilometers wide. The comet's nucleus, the solid object at its core, was estimated by astronomers to be only about 15 kilometers across at most. This means the entire comet was just 4.4% of the width of a single pixel on the detector. It's like trying to photograph a single human being standing in San Francisco using a cell phone camera in New York City. No matter how perfect your focus, the light from that object will never fill more than 1 pixel. The fuzzy dot wasn't a blurry image of the comet, it was the entire image of the comet. Its faint light smeared across one single sensor element. It was a technical ceiling, not a conspiracy. The camera could only give a fingerprint, not a portrait. High-rise goes dark. If Europe's camera wasn't up to the task, surely America's best would deliver. All eyes turned to NASA's Mars Reconnaissance Orbiter and its legendary high-rise camera. This is the instrument that can resolve features as small as 30 centimeters on the Martian surface from its 255-kilometer orbit. Its power is, honestly, unparalleled. The team lead for HiRISE, planetary geologist Alfred McEwen of the University of Arizona, had plans to capture what would have been the most detailed image of an interstellar object in history. With its angular resolution of 1 microradian, HiRISE could have achieved a pixel scale of 30 kilometers at the comet's distance, good enough to put several pixels across the nucleus and reveal its shape. But just as 3I/Atlas made its closest approach, HiRISE went dark. The official reason given was a US government shutdown that had begun on October 1, 2025, freezing all non-essential operations as part of the fiscal year 2026 budget impasse. Command uplinks to the orbiter were halted, data downloads were stopped. HiRISE team member Candace Hansen-Koharchek confirmed over 300 planned observations were lost, including the critical 3I/Atlas sequence. While plausible, the timing felt incredibly convenient to a public prime for suspicion. The crown jewel of Martian imaging was sidelined at the most critical moment imaginable. Radio silence. NASA's silence was deafening, but they weren't the only ones who went quiet. 2 other powerful orbiters were perfectly positioned to observe 3I/Atlas China's Tianwen-1 and the United Arab Emirates HOPE mission. Both had been tracking the comet on its approach. Tianwen-1 carries a high-resolution camera capable of imaging Mars at a resolution of 0.5 meters. The HOPE orbiter, managed by project director Omran Sharaf, has the Emirates Exploration Imager, or XI, a multi-band camera that could have provided crucial color data on the comet's coma. Yet in the days following the ESA image release, neither the CNSA nor the UAESA published a single frame of data. No press releases, no technical updates, not even a statement confirming they had attempted an observation. This coordinated silence from 3 independent space powers was, for many, the most damning piece of evidence. Experts in international space policy, like Professor Svetla Ben-Itzhak, have noted that while agencies often keep data proprietary, such a complete information blackout on a major public interest event is highly unusual. Why would 3 nations, often competitors in space, all simultaneously withhold their data? The lack of information felt less like a coincidence and more like an unspoken agreement.
The image wars.
When the professionals go quiet, the amateurs get loud. In the vacuum left by the silent space agencies, a global network of amateur astrophotographers began releasing their own images of 3I Atlas. These images, often the result of stacking dozens of 300-second exposures from 14-inch telescopes, appeared to show far more detail than the official ESA photo. Some claimed to see a distinct star-like core, a faint green tail, and even jets of gas erupting from the nucleus. The internet split into two camps. One side, championed by skilled imagers who produce work rivaling professional observatories, like Damian Peach, argued that citizen science was outperforming billion-dollar missions. The other side, composed of professional astronomers like David Jewett, warned that these details were likely illusions, or artifacts. They explained that techniques like aggressive sharpening and AI upscaling, which claim to boost resolution by 400%, can't create new information. They amplify digital noise and can turn random pixel fluctuations into false structures. The debate became a crash course in image processing, with terms like point spread function and signal-to-noise ratio trending on astronomy forums. Without official data as a baseline, the line between discovery and delusion had become, well, hopelessly blurred.
Perseverance streak.
While the world looked to the orbiters, the most intriguing clue may have come from the Martian surface. At the Jet Propulsion Laboratory, Justin Mackey, the imaging scientist for the Perseverance rover, authorized a unique observation. The rover's navigation camera, or NavCam, was pointed toward the constellation Ophiuchus for 10 minutes, taking a sequence of exposures as 3I Atlas was predicted to pass overhead. The raw frames revealed a single faint streak, just over a pixel wide, cutting diagonally across the image. The math was tantalizing. At its known speed of 90 kilometers per second, the comet would have traveled exactly 54,000 kilometers during that 10-minute window. A distance that perfectly matched the streak's angular length if it was the result of motion blur. It seemed like confirmation. But rover operations lead Vandy Verma later noted a catch. The same streak could be produced by a much closer object, perhaps a 10-centimeter piece of orbital debris from a past mission like Mars Global Surveyor, moving at just 7 kilometers per second over a shorter exposure. Without the full FITS data headers to confirm the exact exposure timing, the streak remained a 54,000-kilometer question mark, the first piece of hard but ambiguous data in a sea of speculation.
Wow signal link.
A blurry dot is one thing. A straight line to the most famous potential alien signal in history is another. As trajectory experts plotted the path of 3I Atlas through our solar system, they uncovered a coincidence that was just too stunning to ignore. The comet's path, when traced back, pointed to a location in the constellation Sagittarius, less than 2 degrees away from where, on August 15, 1977, astronomer Jerry R. Amon detected the legendary WOW signal. A powerful 72-second radio burst at 1420.4056 megahertz that has never been explained. Immediately, online forums lit up with calculations. For an object to produce a signal that's strong from its current distance, it would need a 2.2 gigawatt isotropic transmitter, the equivalent output of a large nuclear power station. The alignment was so perfect, so poetically resonant, that it felt like it had to mean something. Yet, inexplicably, major radio observatories like the SETI Institute, whose iconic scientist Jill Tarter has long advocated for such listening campaigns, announced no coordinated effort to listen for signals from the comet along the hydrogen line, the very frequency of the WOW signal. The silence was no longer just optical, it was now radio silence right when the stakes were highest.
Approaching perihelion.
The mystery is reaching its peak, yet the main character is about to leave the stage. On October 29th, the enigmatic object known as 3I Atlas will reach perihelion, its closest approach to the Sun. It will plunge to a blistering distance of just 0.3 astronomical units, well inside the orbit of Mercury. For the following 38.5 hours, it will be lost in the intense solar glare, a period astronomers refer to as a blackout. This impending information vacuum is allowing every theory, from the mundane to the extraordinary, to flourish. Some astronomers predict the object might completely disintegrate under the intense solar radiation which will heat its surface to over 400 degrees Celsius. But others, including those from Avi Loeb's Galileo project, wonder if this blackout could be used to hide something else, a deliberate maneuver. The Galileo project has put forth a compelling theory. An engineered course correction of even a few dozen meters per second, masked by the sun's gravity, would be definitive proof of an artificial origin. In anticipation of this, the project has announced a plan to use the Allen telescope array to listen for any telemetry pings the moment 3I Atlas is expected to re-emerge from behind the sun's limb. The world will have to wait. The approaching blackout is the ultimate cliffhanger in a story already short on answers.
The November tests.
The sun won't hide the truth forever. As 3I Atlas is expected to re-emerge into view in early November, a new phase of the investigation will begin. This will be a checklist of pass-fail tests for the object's authenticity. First, astronomers will work to build a detailed light curve, monitoring its brightness for any surges that could signal fragmentation. Second, its trajectory will be measured with extreme precision by the Minor Planet Center, which will look for any deviation from the predicted path not accounted for by natural outgassing. Meanwhile, another mission is waiting for its chance. The European Space Agency's JUICE spacecraft, currently on its way to Jupiter, is scheduled for an observation window between November 2nd and 25th. Its advanced instruments, including the Janus camera, promise a fresh look from a completely different angle, at a distance of about 0.4 astronomical units. Though JUICE will be farther from the comet than ESA's Mars orbiters were, it will have the advantage of observing 3I Atlas just after its closest approach to the Sun, when it is expected to be in a highly active state. However, due to the vast distances and anticipated low data transmission rates, the full dataset is not expected to reach Earth via ESA's deep space antennas until February 2026. For now, the mystery of 3I Atlas is set to continue. So, what is 3I Atlas? Is it a natural interstellar comet that arrived at the worst possible time, a victim of technical limits and bad timing, or is the blurry dot, the synchronized silence, and the impossible coincidence of the wow signal pointing to something more profound? The official story tells us of limitations, but the missing data tells a story of its own. We were given a front row seat to one of the most significant astronomical events in human history, only to have the curtain drawn at the critical moment. The truth remains out there, hidden in the noise of a blurry image and the silence of the world's greatest observatories. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Until next time, keep looking up InnoVision tech. A comet that shouldn't exist just forced the James Webb Space Telescope into emergency mode, and its data confirms a chemical nightmare breaking every rule in the book. The numbers are terrifying astronomers, pointing to something far stranger than a simple interstellar visitor. Is this object even natural, or is something else hurtling straight for us? The stakes only get higher from here. Let's explore this together. Emergency override, Webb's unprecedented response. What does it take to derail the most powerful space telescope ever built? On August 6, 2025, we found out. The James Webb Space Telescope slammed into emergency mode, pausing its entire science program for the first time in years. This wasn't a scheduled observation, it was a high-stakes director's discretionary time override. A procedure so rare it's only the fourth such event since launch in 2021. The target, an interstellar object designated 3I Atlas, ground-based telescopes had just flagged it for accelerating in ways no one could explain, its spectrum flashing with unexpected metals. The call was authorized directly by the Space Telescope Science Institute director, Dr. Kenneth Sembach. The chain of command was short and swift, bypassing the usual committees that schedule Webb's time months in advance. The risk was immense. Webb's schedule is a precise ballet of fuel and orbits. A single, unplanned maneuver to observe a target for 5.3 hours could cost a week of other science. But the window to catch 3I Atlas was closing fast. Its trajectory was shifting by the hour. The command was uploaded and the telescope pivoted, its near-infrared spectrograph, NIRSpec, locking onto a target that was rewriting astrophysics in real time. This wasn't a routine target of opportunity, it was a scramble to observe an object challenging our fundamental understanding of visitors from other star systems. Early activity beyond Jupiter's orbit. Here's where the story gets strange. Comets are supposed to be dormant deep freeze travelers. They wake up when they get close to the sun, typically inside Jupiter's orbit at 5 astronomical units. But 3I Atlas started showing activity far out, at 6 AU from the sun. That's nearly 900 million kilometers away, where temperatures hover around a frigid 110 Kelvin. The first hints came from the Pan-STARRS survey in Hawaii, led by Dr. Ken Chambers, which noted a faint, persistent brightening. It wasn't just a flash, the object was waking up. Then the 8.1-meter Gemini South telescope in Chile confirmed it. 3I Atlas was already sprouting a tail, a ghostly limb of gas stretching hundreds of thousands of kilometers. This is not how comets are supposed to behave. For comparison, 2I Borisov, discovered by amateur astronomer Gennady Borisov, began its activity much closer. The early outgassing of 3I Atlas suggested its engine wasn't the sublimation of water ice. Something far more volatile was driving this activity, a clear sign this visitor came from a place with a very different chemistry. It was the first clue that 3I Atlas was a messenger carrying a very strange message, one that began long before it should have. The carbon dioxide anomaly. The moment Webb's NARSPEC instrument locked on, the chemical picture came into focus, and it was a shock. The spectrum was overwhelmed by carbon dioxide. In the cold depths of space, CO2 ice turns to gas at much lower temperatures than water ice, explaining the early activity. But the sheer quantity was staggering, with a production rate exceeding 10 to the 28th molecules per second. Webb's data revealed a carbon dioxide to water ratio of 8:1. Let me put that in perspective. A typical comet from our solar system like Hale-Bopp has a CO2 to water ratio of about 20%, or 0.2 to 1. The interstellar comet 2I Borisov had a ratio of about 0.4 to 1. 3I Atlas was 20 times more CO2 rich than Borisov. As Dr. Neil Dello Russo of Johns Hopkins APL, an expert in cometary composition, would note, this is completely unprecedented. The data was undeniable, with the telltale signature of CO2 at a wavelength of 4.26 microns burning bright and broad. Water was there, but only as a faint afterthought. This wasn't just a comet with extra CO2, it was a body fundamentally built differently, pointing to a birthplace where water might be a trace element, a type of protoplanetary disk our models barely account for. Nickel without iron, an impossible chemistry. But the carbon dioxide was just the appetizer. The main course was a chemical puzzle that sent shockwaves through the astronomical community. Webb's spectrum showed clear, strong signatures of metallic nickel. At first the team suspected an instrument artifact, but the lines held firm, confirmed by the Very Large Telescope's UVS spectrograph operating at a resolving power of 80,000. The nickel was real, with a production rate of 10 to the 21st atoms per second at 3.8 astronomical units. But here's the impossible part, there was no iron. In every celestial body ever studied, the cosmic abundance ratio is about 15 parts iron to 1 part nickel. 2I Borisov followed this rule. 3I Atlas shattered it. The data showed that nickel outnumbered iron by more than 40 to 1. Imagine finding a pure platinum nugget with no trace of other platinum group metals. That's the scale of this anomaly. Spectroscopists like Dr. Dennis Bodowitz, an expert on cometary composition, would be stunned. The nickel lines at 3,415, 3,524, and 3,525 angstroms were unmistakable. But the spectrum was flat, where iron should have been. One fringe theory suggests the formation of nickel carbonyl, a highly volatile molecule, but for this to happen without its iron equivalent defies all known astrochemistry. Trajectory anomalies and acceleration spikes. As the chemical data was being analyzed, the teams tracking the comet's path were facing their own bewildering problems. 3I Atlas was not following the clean, predictable arc of gravity. It was accelerating, showing a non-gravitational change in velocity of nearly 0.12 meters per second squared over just 72 hours. While comets do this, the force is usually gentle. The acceleration of 3I Atlas, however, wasn't smooth. The trajectory, tracked by the Minor Planet Center, showed tiny, sharp jumps. This recalled the mystery of Oumuamua, whose own non-gravitational acceleration was famously detailed in a 2018 paper by Marco Micheli. But this was different. For an object estimated to be 11 kilometers across, this is like watching a mountain suddenly shift course. The Pan-STARRS survey team ran every diagnostic, checking for software bugs or errors in their astrometry. The data was solid. The acceleration was real. It meant the forces acting on 3I Atlas were not just coming from the sun. Something else was at play, something internal, or something about its structure that allowed it to move in a way that defied our models, deepening the mystery and fueling speculation that this was no ordinary cosmic iceberg. The lighthouse effect. Mechanical light curves. The weirdness didn't stop with its chemistry or its path. The way 3I Atlas reflected sunlight was just as puzzling. Photometric data from Gemini South and the TESS Space Telescope revealed a periodic brightening, a sharp pulse of light that repeated every 7.2 hours with almost mechanical regularity. It was like a lighthouse beam. A slow, gentle tumble is expected from an outgassing comet. But this was different. The brightness changed by over 2 magnitudes, a factor of 6, which is an extreme variation. The period was too constant. Dr. Karen Meach of the University of Hawaii, who led the team that characterized Oumuamua's wild tumble, would find this regularity highly unusual. For a normal comet, the spin should slow as it loses mass, but the 7.2-hour period remained locked in. Astronomers tried to model it as a spinning, elongated object, but the sharp rise and fall of the light curve didn't fit well. Other models suggested a hollow or even a sheet-like structure with sunlight glinting off a large, flat, reflective surface. The parallels to Oumuamua were impossible to ignore, but 3Y Atlas was bigger, brighter, and its light curve was even more pronounced, more rhythmic, pushing the boundaries of what a natural object could be. Ancient sky metal. Historical context. The idea of metal falling from the sky isn't new, it's woven into our history. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't possibly have smelted. Analysis of artifacts from the Gertza tombs reveals the secret. The beads contain nearly 30% nickel. No terrestrial ore has that composition. The only source was a rare type of meteorite called an ataxite. A similar story is found in Tutankhamun's tomb. Buried with him was a dagger with a blade of meteoritic iron containing 11% nickel and 0.6% cobalt, a composition detailed in a 2016 study in Meteoritics and Planetary Science. This iron from heaven was incredibly rare. The Babylonians also watched the skies, and their cuneiform tablets speak of burning stones as omens. The Akkadian word for iron, and bar comma, is sometimes translated as sky metal. These cultures didn't understand the chemistry, but they knew this metal was different, special, and came from beyond their world. They understood that when the sky delivers something new, it can be both a wonder and a warning. Today, astronomers use powerful telescopes, but the core question remains. When an object arrives with a signature that defies explanation, what message is it bringing? Avi Loeb's challenge to consensus. As the data on 3I Atlas circulated, one voice cut through the cautious scientific debate. Harvard astrophysicist Avi Loeb. He had already made waves with his controversial hypothesis that Oumuamua could be an extraterrestrial artifact. Now, faced with 3I Atlas, he was even more direct. In a widely read blog post, he posed a blunt question: what natural process can produce a comet with pure nickel and no iron? He pointed out that separating these elements requires complex industrial processes. In the cosmos, it's considered impossible. Loeb connected the dots: the impossible chemistry, the erratic acceleration, the clockwork light curve. He argued that we must consider the possibility that we are looking at technology, a central mission of his Galileo project. His critics urged caution, but Loeb's position is that the anomalies themselves are the evidence. He contends that clinging to a natural origin explanation when the data contradicts it is unscientific. His challenge forced the conversation into the open, pushing the debate beyond academic journals and into the public square, demanding that the artificial hypothesis be considered on its own merits. Scientific community divided. The case of 3I Atlas split the astronomical community. On one side were scientists working to find a natural, if exotic, explanation. Dr. Alan Stern, principal investigator of the New Horizons mission, had previously proposed that Oumuamua could be a nitrogen iceberg from a Pluto-like exoplanet. Perhaps 3I Atlas was a carbon dioxide iceberg from a similar world. Others, like comet expert Dr. Matthew Knight, argued that the non-gravitational acceleration could still be explained by powerful localized jets. On the other side were those emboldened by Loeb, who argued that we had to take the artificial origin hypothesis seriously. They pointed out that a light sail, a thin, reflective sheet, could neatly explain both the sharp light curve and the acceleration. No one was claiming definitive proof, but the idea that 3I Atlas might be a probe, or a fragment of one, was no longer a fringe theory. It was being actively discussed. Peer-reviewed journals and online forums buzzed with debate as every new piece of data was scrutinized. The object was a cosmic Rorschach test, and what you saw depended on how willing you were to challenge fundamental assumptions about our place in the universe. NASA's high anomaly classification. Behind the scenes, the official response was one of cautious urgency. While public statements remained measured, NASA's Planetary Defense Coordination Office, led by Officer Lindley Johnson, quietly flagged 3I Atlas with a special designation high anomaly. This classification is typically reserved for near-Earth objects whose behavior is unpredictable. But in this case, it was for an object whose very nature was in question. It wasn't a threat in terms of impact, but it was a scientific wildcard of the highest order. Internal risk assessments using systems like Sentry-2, usually focused on collision probabilities, were repurposed to track an enigma. The official line from NASA remained consistent: more data is needed. Extraordinary claims demand extraordinary evidence. Yet in private, even the most skeptical scientists admitted this object was unique. The data was being triple-checked and distributed to a wider network of researchers. But until a consensus emerges, 3I Atlas remains an official mystery, an object whose strange behavior has earned it a unique place in NASA's catalog of cosmic visitors. So what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system whose chemistry is alien to us, or is it something more? The evidence is tantalizing and deeply unsettling. An object that moves on its own, shines with a mechanical rhythm, and is made of materials that shouldn't exist in nature. It could be the first definitive proof that we are not alone in the universe, a piece of technology from a civilization far beyond our own. For now, the answer hangs in the balance, locked in the data, awaiting the next observation that could finally tip the scales. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching InnoVision Tech.